I think we're live. I think we're actually live. So, here's the thing. We're gonna work on the. I always do this. So, hi, my name is Zach, and I'm a freelance. Let's start that from the beginning. Hi, everyone. My name is Zach, and I'm an open source software developer. And I'm trying to use December of 2025 to get really serious about because they say if you're serious about building your software, you should be serious. You should be the whole hardware. So this month I'm using Advent of Code to kind of get into building or rather doing digital design and designing ICs using Verilog. And in the aid of that, I've been using the hands-on FPGA course by TinyVision. This is where it is. You can find this. This is a hands-on FPGA class, and today we're going to tackle week 3 and actually the task in week 3, which is building a binary counter. This should be quite simple. This should be quite straightforward. We should be able to do this really quickly. I don't think it's the surrounding stuff that's going to be not easy, but we'll find out how to do this, how to fix it up. So I was sort of going through how I was considering how I wanted to do this, and then I come to realize that initial might not be synthesizable. The initial block is not synthesizable. So basically, it cannot be converted into hardware with digital elements. Hence, we can't use them other than in simulations. So we basically have to use something like an assign or something. I guess. Because look, here's the thing. So in our other module, okay, we didn't have an initial begin here, so that's fine. So that's okay as well. So we have to find a way of going through without doing initial begins, and I think we will do things like def assigns or something of the sort. Assign, and there's a few keywords that were introduced here. That might help us, I guess. Is it all in parallel? There's a few keywords that were introduced on how to set. There's things like parameters, I guess. So we can use parameters to set stuff. Yeah, you see, you can use a parameter to set a with 70, and then we can use it to actually set registers as we go along. And I don't know if parameters are synthesizable. I don't know if parameters are synthesizable, so we'll just have to learn slowly about that. But I think we can use like def assigns and assigns when beginning and things of the sort. And I'm trying to see if there's something that will show us how to. Yeah. So you see this initial this is not synthesizable. So we can't have this in an actual thing. So how do we set defaults? I think you have to do like an assign at the beginning of it. Probably. Let's look at the Verilog quick reference. Is there something like def assign? Def assign. Assignments, continuous assignments. There's no page 18, so 10. Chapter 10 is probably going to be here. 10, okay, good, 10 is going to be here. Continuous assignments. Control plus plus. Continuous assignments. What are continuous assignments? This naming blocks always begin, initial forever. We don't want that. This is not synthesizable. Always is always procedural blocks. Verilog always block is always synthesizable. It looks like it is synthesizable, so I guess we can do something like that. But we don't really want to do that. We want to set it up, and then we want to be done with setting it up. Yeah, regular assignments. So this one. This, you see, this sets that. Okay, cool. And then as you go on, the clock keeps changing. And then, but there's an initial begin here, which we can't really use. This is fine. So we're gonna have to find a way of doing this kind of stuff without initial begins and such. Let me tell the Discord group that I am actually live. Jerome. This is live. So let me tell the Discord group that I'm actually live, and let's leave it at that. So cool. Let's keep going. So anyways, we'll come back around and we'll find out a way where we land this. Okay, because previously I've done like silly stuff before, and I now realize this is why it was kind of biting me, because I've done this tiny CPU before, and this is the problem of like, this is both the problem and the advantage of like jumping into stuff all the way in. But in my actual synthesizable, I can say that word now, synthesizable block, I had like some ROM instructions, and I would set them up, and here they are, and I use an initial begin. But this has a test bench that wasn't corresponding to what the hardware was doing, so the simulation was off from the hardware. So this is kind of something that I needed to sort out. So I can't use that. I can do something else, but not that. Probably do something of a sort and set them as, because I can do this. So I can do some setup at the beginning, and this is a blocking assignment. So I can set this up. I can do all of this as blocking assignments, and then not need to use this later. But I need to find a way of doing it so that it is, I guess, sequential, and we don't want to do it at an always or something. So we're gonna find out how to make those match. And in looking at this, I realized, because we're gonna start looking at pipelines now. In looking at this, I realized I've worked with things like bus matrices, and that's a little advanced. I didn't know I'd done that yet. But sometimes you do stuff and then you only understand it later. Anyways, let's go back to our thing today. So, what are we doing today? We're working on this challenge. Use circuitverse, or preferably system verilog, to create a 4-bit binary counter. This should count the following sequence: 0000001, 0010, and then all the way to 111, and then it would roll over to 000. So this is going to be rather easy, I think. So let's go make a project, and then let's see how it works out, eh? Let's go make a project and see how it works out. So we want to do ghosting. Yeah. Let's get ghosty started. And yeah. And then we're going to go cd documents, eng. And then let's ls, and then we should go like, we made an RTL adder, RTL binary counter. Okay. RTL binary counter. Let's do that. So the RTL binary counter, and then let's clear that, and then let's initialize a new project for the Arduino. Control R. Up here, create. Yeah, cool. Top module. Let's make the top module main, which we won't use. Let's do that. So that should set up a thing really quickly. ls. Up here init has been set up. But now we want to do a binary counter module. So nvm. Let's set this up. Let's make anyhow we want to do like a main.v and then in here we're gonna do something like module main, and then this can be that, and then this can be like end module. For now, this is going to be okay. And then in here we can do something like reg a, something like that. Unless I need to do this, and I can do that, and I can do that. I think that's how we can do a binary module, and then you just need to end it, and then it's fine. And then obviously we want this to be default. We want the default net type to be null. And then in here we're going to do a binary counter module. Binary counter. This is actually the module we're going to be working in. We just made a top module so that we can I can actually start working on the same project at some point. I should like just keep all the stuff in like an Advent of Code FPGA project. But things are gonna get weird, and then we're gonna like work on stuff, and we're gonna not know where it is. So GitHub is free. Binary counter. Okay, let's do that. And then in here, let's say module binary counter, which is going to be really simple counter. Module binary counter. This doesn't really take much. We need a clock. We need a clock. And that's not gonna actually. Let's just delete this here. Let's just work everything in main. Let's do everything we need to do in main. So the first thing we want to do is we want to use the resident clock on the UPDuino. So the UPDuino, as we discovered the other day, has where is this? The UPDuino, as we discovered the other day, which is the 301, which is the PDF. Where's this PDF? Has onboarded. Okay, cool. Sorry about this. Let's zoom in. We have a 12 megahertz clock over here, and this 12 megahertz clock goes into IOB 25B, as you can see here, 25B, and 25. The IOB 25B G3, 25B G3, IOB 25G3 goes into 5 here. Okay, goes into 5, but where's that? What is 5? IOB 25B G3. That's pin 20, as you can see here. So it goes into pin 20. So we need to make a PCF that uses pin 20 as an input, probably, because look. So the first thing we need to do is get a clock, so that whenever our clock runs, we need to be able to use this clock. Every time the clock runs, we would like to increment the count. That's how our binary counter is going to work. So input. So clock input here, and then we're going to see something like input into the FPGA CLK, and then let's say that's let's leave it at that. Okay, but this would imply that we need a pin constraints file. We always need one anyways. In the PCF. And then here we're gonna do like set IO CLK. So I'm gonna tab CLK tab 20. So use pin 20 use pin 20 as an IO. But then remember we said it, we labeled it as you can remember here in the main, we labeled it as an input. There's an input of a clock there. And okay, so now what do we want to do? The next thing what do we want to do? We want to declare, let's think about it. We want to declare a 4-bit register. Because look, let's look here. Let's look here. So we want 4 bits in a register. So we want to, and we can't use a wire because that's a bus. A wire is a bus. Wires versus registers. Wires are buses. Where's that? So there's this is going to be in a different place, but let's look at it here. As you can see, I was looking at that. So there is something. There is a document, or maybe with two probably. Yeah, there's this. So wires, and I would wanna go here, and everything is a wire. Number one, what is a wire? A wire is just a connection. It's basically a connection between 2 points. But wires cannot remember stuff. Wires are they cannot remember stuff. But you might have something that has several lanes. So we could go wire, and then we could set it to 4 lanes or 7 lanes or whatever lanes, however many lanes we want. But then this is just a connection. It is not really. It's not really a register. We want something with memory, something that remembers what it was, so that when we increment it, like the challenge says here, we want something that remembers what it was, so that when we do actually increment it, we can observe changes on it, and then we can go monitor it on that. So I think the best thing to do is to declare some sort of register inside this module, inside this main module. What we want to do is declare some sort of register. I'm gonna do that. My word, something is up. Anyways, let's do some register here, and this register is going to be let's make a tab, and then we're gonna go. This register is going to have a capacity of 4, and we can name it. Value. And we're gonna set it to 0. Okay, that's kind of the stuff. So we're gonna give it like an initial value of 0. So this is a blocking assignment. And then the next thing we want to do is we want to just. So this can be. We can actually set it to. Let's set it to this. For that be 0. What does this mean? So 4 binary, 1, 2, 3, 4. Okay, you can also just do the 1 like that, but let's go more explicit. So let's set it to the initial value of that. As you can see, it says we want to start. Okay. And then now, since we have a clock coming in, what we want to do is whenever the clock blips, whenever we get a rising edge, this is the thing that we covered in the other part, in the NAND land clocks. NAND land setup and hold time. Yeah, this setup and hold time. So what we want is whenever the clock goes on a rising edge, we're going to do an operation. We're going to set an operation here whenever it goes on a rising edge. So whenever it goes on a rising edge, and as we remember from the presentation by the lovely Venkat Rangan, from the presentation slides, module 3. From the presentation we had here, see at positive edge, and I think this was described somewhere, something like that, whatever. Yeah, all changes happen on the positive edge of a clock. Okay, and we already have a clock, so we want to watch for the positive edge of a clock. Always always, and then in this always, what we want to do is check at, let's say, pose edge of let's say CLK begin. So this is now going to be some sequential code that we want to be executed. This is mostly going to be, this is going to be our module. So let's look at this. What is it? We know what an input is because we know that from the other part. We know what a register is because we know registers from this lesson 2 here. Lesson 2, registers. Registers can only be assigned in always blocks. Always blocks may consist of one statement or many statements between a beginning and an end pair. So we could probably, because we only want one statement, because we only have one statement to really apply, we don't need an end here, basically. And this means we don't need a begin. We can just do that, okay? And then we can do some operation, assign value, always like that, assign value something, okay? There should be an operation somewhere here, basically. This is what I'm saying. Assign value, and then assign value, we can go like, I'm thinking, because we can't reuse it. We can't reuse it. Do we need 2 of them? We can't really reuse it, so we look. Look, it's reused here. So can we reuse it? It's reused it again. Only use that in a combinatorial always. So we want to look at actually Verilog assignments before we go on, because we want to learn about assignments in depth before we keep going. Let me see. Is there any questions? Hi, hey, Just Funk. What's up? What's FPGA? Hi, Just Funk. An FPGA is a field programmable gate array. Glad to check comments. Just Funk. Welcome. I should have checked this earlier, so I keep not checking them, and I'm sorry about that. I'm really sorry about that. So if you're around, Just Funk, FPGA is a field programmable gate array. So this is hardware that is reconfigurable in the field, or rather without, an MCU is made to do a specific thing, and an FPGA can be changed. It can be changed. It's the hardware. It's reconfigurable hardware, basically. This is a good one to go. What's an FPGA? What is an FPGA? Let's look at it. Field programmable gate arrays are integrated circuits, often sold off the shelf. They are referred to field programmable because they provide customers the ability to reconfigure the hardware to meet specific use cases after the manufacturing processes. This allows for feature upgrades and bug fixes to be performed in situ, in the place, which is especially useful for remote deployment. So FPGAs contain configurable logic blocks and set of programmable interconnects that allow the designer to connect blocks and configure them to perform everything from simple logic gates to complex functions. So like your microcontroller comes with some features. Your microcontroller could come with a certain amount of memory, a certain amount of inputs and outputs, and so on and so forth. And FPGAs gives you some sort of thing called a fabric that you can shape up in whichever form or shape that you want, so that it ends up becoming the thing you want. So Um, let's think about it. So what we wanted to check out, so let's go back. What we wanted to check out are assignments, because we want to know, first of all, why is this telling us only to use that? This is a blocking assignment. Why can we only use this in an always block? And how come there's a registers can only be assigned in an always block? So what is a sign? And what is this? What is the difference between this and that? Anyways, it says here, there's two basic types, both set with an always. Why use registers? Wires have no memory. Only registers can hold state data. There's two basic signs, both set with an always combinatorial, like wires. A equals B, like that. And then this is a form that can be easier to read when the logic becomes complex. Synchronous only changes values on a clock. Aha! So we need this one. So what is the difference between that assignment and this assignment? That's kind of the thing we want to find out at the moment. If that makes any sense. Yeah. If that makes any sense. That's what we want to find out. Stream settings, stream L. Okay, cool. That's fine. So, what is the difference between this combinatorial and synchronous? So, let's look at assignments. So, Verilog assignments. Placing values onto nets and variables are called assignments. A net is a wire, and a variable is a register. Okay. An assignment has two parts: right hand side, and the right hand side and the left hand side, with an equal symbol. This one, so with an equal symbol like that, or like they say, with a less than or equal symbol in between. I should zoom in here so that people can see. With an equal symbol or a less than or equal symbol in between. So we don't know yet what those are yet. So assignment type, there's a procedural one. This is variables. It could be one variable or many groups of variable. It could have a bit select or a part select or a vector register or an integer or a time variable, a memory word or a concatenation of any of the above. Okay. And then this is a continuous. This is you're always setting this. This is always happening. This is always being set as a FPGA. Like this is the parallel part of the FPGA thing. This is always being set. So this applies to a net, a bit select, and a concatenation of bit select and part select. So it feels like this doesn't apply to a variable. And then there's procedural continuous, net or variable. So you see, this is a net. A net is a wire or a bus, something of the sort. Okay, so a wire or a bus, that's a net. A wire or a bus, that's a net. Where are we? Verilog assignments. How deep is this? This is after blocks, procedural blocks, initial block, always block, Verilog control blocks, and stuff. Anyways, so a procedural assignment occurs within the procedures such as always, initial, and task, and functions that are used to place values onto variables. Okay, cool. The variable will hold the value until the next assignment of the same variable. Okay, cool. So you can use a procedural block, something like an always or an initial, to set a variable, and it will stay in that. It will hold that value until such a time that some other block or some other thing assigns it to that. So let's look at this one. The value will be placed onto the variable when the simulation executes this statement at some point during simulation time. This can be controlled and modified the way we want. This can be controlled and modified the way we want by use of the control flow statements such as if, else if, case statement, and looping mechanisms. So look at it. So there's a register here, which is an 8-bit register. There's an integer here, and there's a real period here. And then what happens here is in on initial begin, this is at the begin, at the start, we set the register to that hex value and the period to that value and the count to that. And then always whenever the positive edge of a clock does, we just increment the count value. And then variable declaration. So where we that looks okay. So wait. Did we just skip some stuff? Okay. Yeah. So there's a few here, and we don't know. So there's this kind one, this kind, and then there's this kind. This is y is LHS, and the constant is 100s. This one is f is equals to that and that, and then this doesn't need an assign. Or why does this not have an assign on it? And what does the assign keyword do? Yeah, it seems like assign is the same as the thing. Yeah. What is this? It's a continuous assignment. Imply that whenever so what is a continuous assignment? Continuous assignments imply that whenever any change of the right hand side of the assignment occurs, it is evaluated and assigned to the left hand side. So whenever anything changes, whenever A or B changes, this is the parallel part of FPGAs. So wherever else in your design you're using A and B, whenever those things change, this assignment will happen. Assignments to register data types may occur within always initial task and functions. These expressions are controlled. Let me do that. These expressions are controlled by triggers which cause the assignments to evaluate, such as a clock. Like it's here. Always at reset, do that. So this is a procedural assignment, and this is a and then do they describe procedural blocking assignment? Okay, cool. Let's just look through this. These expressions are controlled by triggers which cause the assignments to evaluate. The variables to which the expressions are assigned must be made of bit select or part select or whole elements of a register, integer, real, or all time. These triggers can be controlled by loops, if else constructs. Assign and deassign are used for procedural assignments and to remove the continuous assignment. Okay. Force. What's that? Okay. So where do I go after that? Where is this? What is this I'm looking at? Tasks and functions. That goes to 11. But yeah. So this is coming from 11.0. So here. Force and release are also procedural assignments. However, they can force or release the values on the net or data types and registers. So a blocking assignment, this means it will happen, and then this doesn't. It won't wait for this to happen for it to go to the next one. Okay, fair. That's okay. So here I can do like something like that, and then I can say a value. So value plus I think it's 1b1 or something. One bit binary. Yeah, 1 bit binary. 1b1. And because we've actually looked at this before, because yesterday, whenever we looked at the code before, whenever we overflowed, it would rollover. Yeah, so cool. So the problem is, or rather the problem here is, or rather, Control Shift T, and we can do an Appio build. Appio lint maybe. Let's see if that lints. Why is it expecting that? Why can't we use that? Why can't we use that? Oh, I see, because then we don't need to use the assign keyword. Okay, fair. So these don't go together. But let's look at the quick reference quickly. Yeah. So the assign keyword is not here, is not used here. Okay, cool. So we don't need to use the assign keyword if we do this. Let's lint. Okay, cool. So it lints okay. So that's fine. So now let's think about building a test bench. So let's look at the test bench we built the other day. We had this, and then we built a test bench like this. But this one had inputs and outputs, and we don't even need an input and an output. So let's actually go into here, and let's make a test bench. Main td.v. Let's make a test bench, and in this test bench, what are we going to do? First of all, we're going to set a time scale. 1ns, 1ps. I think so. Pick a second. Yeah, we can space this so that it's okay. And then in here, what we want to do is we want to declare a module main td. And in here, we want to do that, and then we want to say end module. I'm going to close this and open it so that we get syntax highlighting. I know I'll set up my editor so that it works, but for now we'll have to live with that. That's okay. So we don't need anything else in here, really. Really, we don't need anything else. Let's instantiate the main module. So we can do like main DUT. Let's instantiate DUT here, device under test. Okay, cool. And then we don't even need to do anything else in here. What I just want to do here, do we actually end module twice? We just instantiate it, and then we leave it at that. Yeah, so that's just gonna go because of clocks, and then I would like to do a for loop. That's what I want to do. I want to do a for loop so that whenever we don't have to, like, I don't want us to do yeah, let's do a for loop. Let's do a for loop for 20 so that yeah, integer. I really would like to make it so that the thing does itself. So anyways, integer count, clock count is equal to 0, and then let's make some for loop in here for what is it, for clock count is equal to 0, clock count is less than 20, and then let's do clock count is equal clock count plus plus. And then in here we can do, actually we can just do that, and then in here we can do a begin, and then in here we can do an end for this begin. Yeah, so in here now we have a loop in here, and we're gonna use this loop to actually test the we're going to use this loop so that we just watch the clock itself being run. Wait, do we need to pass in? We need to give. So I see my error. So we do need to supply at .clk. I still don't know how to do this, but CLK. We still need to supply a clock. And then in here we wanna do our register CLK and is equal to 0. Set it to 0. So let's add a register here. And then the next thing we want to do is, once we've connected that, let's set this to a 50 megahertz clock. Just for shits and giggles. Set 50 mH Z clock. And then we can go here, always wait 10 CLK is equals not CLK, always wait 10, because hash 10, if we see here, hash is this. Where is it? Hash in Verilog. That's a delay, I think. Verilog syntax. I think the delay, the hash is a delay. I just wanna find it, so I show it to you, so I don't just use stuff that exists by itself. Wait, yeah. Verilog wait. Verilog wait. Delay control. There you go. So a delay control. This. You see this? This means wait 10. This is our thing is not going to be like a very precise thing, but this means wait 10 after a delay of 10 0D units, whatever. So this means wait 10. And basically what we're doing here is we're waiting 10 and we are flipping clock. Okay. Not clock. Okay. That's basically what we're doing. This registers have a default value of 1 bit binary. Registers have a default value of 1 bit binary. So every 50 megahertz, every 50 that we are flipping clock, and because we are flipping clock, our main because we're flipping clock and there's an input that is clock here, we will get a positive edge, and whenever that positive edge occurs, we can observe something here. So the next thing I wanted to do, so that we can actually see what we did, is build some sort of I'm trying to look for comments and questions. So the next thing I want to do is we want to make sure there's no comments. I want to make sure that we have, let's go to the other thing we did. So we want to do a monitor here, basically, and a monitor will be able to peek into the how do I explain? A monitor will be able to peek into the module, our module itself. This monitor can look into the module itself, and it can look at how things are changing. And the nice thing is we can also touch things that are defined into the. Let's actually just copy this. Well, we don't even have to. How do I want to print it? As a binary, as a 4 binary. Okay, I just need to remember the syntax. I want to do a hash monitor, and then in this hash monitor, what do I want to do? I want to say current counter value is equals, and then I want to go like what is it like that, 4b, very log binary print. I think if I'm not I think, yeah, it is 4b. I can do that, 4b, yeah. So I can do 4b, I think so, 4b, and then in here I can do dut dot value. So this is the one from I just want to make sure that syntax is right. Monitor dot. This is the one from dut value, device under test value is this one. There's this register called value, and it's a 4-bit binary. So I wanna see if I can monitor it like that. So the first thing we want to do is, and by the way, we can do this. We can also do this dump vars. We can also do a dump vars, but I would want to do this in a initial begin probably. If we do a dump vars, that will give us a GTK wave simulation. This is something that we're not using yet, but it wouldn't hurt to do an initial. I'll do a begin here because I don't remember internet, and what I want to do here is dump vars, so dump vars, and then I want to do 0, 0, 0, and then I want to do main TB. So this will give us a GTK wave simulation of whatever is happening every time it changes, and we can open a simulation and we can actually watch this visually. So let's actually see. Will this first of all appear lint? We're in lint. There's nothing we've changed. It's okay. Monitor current values. Unexpected monitor. Okay, cool. That's fine. Monitor current value and So something needs to end properly before that. Initial begin unexpected monitor. Are you telling me I don't need to do that? Or I can just use display rather than monitor. Display. Okay. I'm very confused. What did I do wrong? What did I do wrong? And where is clock count actually incremented? Oh, it is incremented. Something is up. Just let's actually do a comment. Let's just go like see if that actually there's some error I'm making before this that should be that's actually making this problem. So how do I make it so that it only goes for 10 clock counts? There's something I'm not doing right here, and this is maybe that, maybe that, maybe that. I don't know if it's a white space. Questions, comments, let me check. None. So it's something in this statement. Looping constructs, Verilog looping constructs, loops, loops. These ports explained, yeah. Anyways, now we just want to find loops. Verilog 4. What did I mess up there? For initial condition, step assignment task, begin, end. It's and what is the thing for begin, end? So there's something in this code that I'm doing wrong. There's something here that I am doing wrong that I wasn't doing when I was doing the other CPU over here. So let's look at this test bench because I've used this construct before. For that, begin. That's it. You want me to do that? You want me to go like at pause edge? Pause edge CLK DUT CLK DUT CLK. Okay. Something is wrong with that. So there's a begin here that something's wrong with that. Something is wrong here. Come on. It's fine. Let's just go again. Yes. So let's actually remove all of that and see what happens. So let's remove that. And let's look at our sample code from a few months ago, and then we need to do an probably does it need to be in an initial begin? Okay. Okay, let's do that. Let's just do all of that. because this one is more than one line, it's gonna be an end here. Okay, and then because that module, there's an initial begin and that's the end for that module. So let's lint. Okay, cool. But that 4 is just after. Okay, cool. So let's up your sim. Dump var is not dump vars, isn't it? Dump vars, dump vars. We use this one at dump vars, yeah. Okay, cool. Something's happening for sure. I'm not passing in the clock. Whoa, it's doing the thing. Okay, I'm gonna remove the dump vars because I don't want to use that, and I don't remember why this doesn't. Other TV, other TV, other TV. So main TV, other TV, main TV. Why didn't that work? So somehow the GTK wave thing is not working for me. Somehow I get it. See. Let's do I have some sort of GTK wave thing that I'm not opening somewhere? I'll remove the GTK wave one. I know this is not working for me, but I don't know why. Up here sim. See? Somehow I'm not getting this window. Let me check on a secondary display. Somehow I'm not getting this window, which is a problem. And if I stop it, it doesn't work. So let's remove this and let's save that, and let's just go like clear. I have a feeling that was the issue. Up here, sim. Build, and then clear that, and then let's try and up here sim. 1, 2, 3, 4, 5, 6, 7. Let's wait. Give it almost a minute. Sometimes these things take time. I could be doing something odd somehow. Let's actually look at the other simulations and think about it. So there's an initial begin here, and then there's an initial begin, and then there's a monitor, and then we can just use a monitor and we do that. So, and then let's look at this one that provided a clock to its test. So we set some clock cycles over there, and then we did an initial begin, and we waited 100 for values to set, and then we went for it. Values to settle. There was just sort of wait here before the initial begin, before everything done, before the for loop. We'll see. You see, it does its job. It does, and this is not good. Why is it 5 bits? Oh yeah, I understand. This is, it's supposed to be 3 bits. 0 to 3. And does it ever set the 1 over here? So that's not a good thing. So here, first of all, in our main, this is going to be 30, and this is not 4 bits, this is 3 bits, because it's 0 to 4. And the other thing I want to do here, is somehow my simulation runs quite slow. Let's save that. And then let's go look at our table here, and then yeah, there's that, and then like let's go in here, and before we do that, let's do 100 weight, just for things to stabilize, like we did here, for initial values to settle, and then let's save that, and then let's go here, and we know this is, yeah, that's the wrong way to do it, so, and this can't be cleared, so control X, control A, control X, Y is yeah, shift T, up here linked, see, that's 3 binary 00 notes. So okay, cool. So here, so that's a 3-bit. So that I do want it to be a 4-bit. Okay, so that's up here linked. That's fine. But then value is a 4-bit. But I want it to be 4-bit. This is amazing, we're learning so much. So what is, okay, this is a test bench. Let's look at the test bench. Yeah. So this is gonna be a O3, so let's look at it. OD, OH. We could actually just, instead of dot, let's actually use, and why is it a 3B1? Let's see, because it's 111 is all the way to F is already representable in up your sim. This is so slow. This is so slow. It's not supposed to be this slow. It really isn't supposed to be this slow. It should at some point finish. So there's something I'm doing here that is really messing up the timing. So let's actually look at this. So this is all set up. This is set up here. This is inside an initial begin. And we do that, and we connect that, and we set this 50 megahertz clock over there. 50 megahertz is not slow. 50 megahertz is not slow. So, and we do that, and then we set this and upwards edge of DTC clock. DT. Are we doing that? Yeah. Perhaps we should check that the clock cycles is more than 0 before we do this thing. Yeah, perhaps we should do that, and then we see, because if we stop now, it's, oh yeah, I don't want it, goes 5 6 7 8 9 A B C D E F O 0 1 2. Yes, it works, it counts all the way to 15 because it rolls over at F and it goes to 0. I don't know why it's not, why wouldn't it show me Verilog print 4-bit binary? Let's look at this. Excuse me. Do I just do binary? Do I just do binary like that? And then we wanted if. What is the other thing? We wanted to wait, because this could be like some sort of little timing constraint that we are falling into. This is sort of stuff that takes ages to learn. So you see this, yeah, we could check that our slow clock cycles, which is our clock, which we might be reassigning clock count. If, see what happens here. Yeah, so we can check for this inside, and this positive edge should be, it's in here, and then inside, before we do the display, we could check for it in here. So if clock count 0, we want that, and we want to do a begin, and then we could do that, and then after this we could go and then we could go that, and then we can do this, and then I want to do up here lint. Let's lint the code up here sim. Let's see. What if we just go here and we go like 2? And anyways, where is that being set? So it's immediately after we do that, generate the clock adjust period that's needed. So this is a 50 megahertz clock. It's made up here, and then this the DUT is connected to the clock over there. And then after that, we wait 100, and then we go in here and we start doing stuff. When we wait 100, we wait 100 before we start manipulating the clock cycles. Let me see. Slow clock cycles is slow clock cycles. Fine. Then wait for the rising edge of the slow clock, and then that's it. And then once we're in the rising edge of the slow clock, we're listening to that one. So this is the 4 that, and then at that we want to do this play. And then this is still going. But if we do a C, yeah, it does exactly what it's supposed to do. It really does do exactly what it's supposed to do. But I don't know why this test bench is behaving like that. It just hangs. Something is wrong. I want to do this. I want to see where this error is actually. And then I want to be up here lint. Is it gonna be happy? Up here sim. Control C. Yeah. So it's not there. Let's look at the time scales. That CPU TV, module TV, main TV. Reg is equals to that. And then we instantiate our DUT, main DUT, times CPU DUT. That's fine. And then yeah, that's instantiated. And then that's instantiated like that. That does not need a comma at the end. That needs that. That's okay. Dot clock is a dot clock. And then we generate a 50 megahertz, which is actually much faster this. Yeah. And then we do an initial begin. We have that set up there. There's the setup here. And then we do an initial begin, where we do all of this stuff. Maybe let's actually look at our main. We could be doing something in our main that's wrong. Always positive edge of the clock. Let's set as that. What if we do that? And then we go like a let's actually also just use a begin, begin, begin. That way we're good here, so that we just not end. And then here we want to do an assign. Up here lint, up here sync. How is the CPU doing it? How is the CPU doing it? I wrote this completely from the manual, not even thinking about it. So let's look at them. So this is just like plain assignments completely, and we did this now. Yeah, and this actually did work, so that was fine. Well, there's a post edge of clock, and why am I getting that warning? So let's do that. Current information. It doesn't like it. Doesn't like it. So we can do that, and we want to do this, and then we want to do that. Reg 03 value is that. So that's the same thing we're doing here. Reg O. Can I just do 0? And then what is wrong? Reg that. Yeah, they're all being set as 0, so there's really no harm there. Up here lint. So this one's happier. This one is a lot happier. This one's a lot happier. Up here sim. What if I do that? And that doesn't like it either. So something's changed. Something has changed enough that okay, cool. So there's this. I did comment this out here, and then I want to do that. Up here lint. Up here sim. Give it a moment. Nothing yet. But if I stop this, we'll get the thing that we want. So I don't know why. So somehow this hangs. Somehow there's a problem here that hangs if begin, and if it does that. So say current value counter is that 1011, and they're displaying completely nice. So it goes 0001 010. So if we look at it, if we look at the challenge that we're trying to do today, we're actually doing the stuff, and it's rolling over from 111 to 000 correctly. If you go 111, it rolls over to 000 correctly. The thing is, we are not actually doing a dump file properly or something. There's something that we're using. What if we do V and then we just go? I wonder if we just go like the I. Let's comment this out, and because this is like something as so we were doing the other day. So because we have this module over here that just uses monitor, and I wonder if what happens if we go like V to the end SY, and then we go KKK, and then it's SP. And then instead of doing that, we just, because we just do monitor, and then we leave it at that, and then we just don't do all of that stuff. Yeah, let's see. Shift T. Up here is lint. up here sim. It works properly. So there's something wrong. Somehow our loop is somehow our loop is wrong, because look, it works completely fine, but somehow our loop, there's something our loop is doing that is wrong. And if I can type I can't. So cool. There's something also that we're not doing correctly here. So let's look at this test module properly. And module, initial begin and module. So it's only one. Maybe one initial begin, a few different initial begins. An initial begin to set some stuff, and then we end that, and then we do another initial begin to do all of the stuff. But there is no defaults that we are setting. So there really is no defaults that we're setting for this. And it's really going the correct way that it should be. What if instead of this we just actually looked at our clock, and then we went like yeah, let's just not use a monitor, and then we can go like that, and then we can do up your lint. I don't know if this is the problem here. Somehow whenever we bring in that loop, and it's gonna be okay now, somehow whenever we bring in that loop, this loop, something goes horrifically wrong. So there's something in this loop that is going, that is being like insanely bad. That is going insanely bad. There's something in that loop that we're using the most wrong way. Yeah, if you see that later and I'm not looking, please let me know. Let me know. So let's look at this test bench. Time scale is set up properly. Is our time scale set up properly? Time scale 1 NS, 1 PS, that's fine. Module main TB, that's fine. That's there, that goes there. Main TB. We instantiate this module, and there's a tiny CPU there, and then we can use, and tiny CPU is duty, and main is duty here. And then we have a clock there, we have an input for the clock, and that, and yeah man, we only have one initial begin in this, so the one initial begin should be okay, and an integer clock count there. Do we want to set this? Do we want to set that after? And do we want to declare it anywhere really? No, not really. So that's fine. And then the initial begin, and in initial begin we wait 100, we check how many cycles have gone, and then we check out the positive edge of CLK. We can also check our own clock, that's fine. And we do a display. Slow clock equals 0, clock count equals 0. Okay. And then let's look at this. Default let type none. Up here lint, that's fine. Up here sim, but this works. And then we can't use the So it's not that. And if we go ram.rf build completely ls, and then yeah, then we go api sim again, doesn't work. And if we use a monitor, obviously it's so if we do that with SKV and we remove all of this, it works. Initial, begin, hash 100, and then end. Exit a module, stop a module, very low. We could do that. Look at what we are learning. Look at what we are learning. So let's wait another 100, which is 100, and then we can go like finish for now. This can be just like that. That's basically what you're telling me. Let's see. It actually worked. It did exactly what it was supposed to. So look, that's amazing. We've discovered how to, first of all, we wrote a binary counter, number one. Second of all, we discovered how to simulate this thing and do it in such a way that we get our terminal back. So you can do a git init. And then, yeah, just let me finish. And then after we did that, so now we have all of that. Let's put this in a module somewhere, in a GitHub. .com Gaiocho. Let's go Gaiocho. And in here, so let's view, and then let's create a repository. Create a repository. This is binary counter. RTL binary counter. Binary counter implementation and test bench. So we actually did well. So yeah, we can do a git init, and then we can here let's make dot getting now. And then in here, let's just ignore all the whole of the build folder. Get status. Get get status. Get add Excuse me. Does this test bench still have the commented out part? No, that's fine. That's okay. That's okay for now. Yeah, and let's look at it. Let's look at it. It just waits 100. Let's look at it. No, because let's do up your sim. Up your sim. It just go. How many does it go? To initialize sim, all of that goes that, and we probably can do a GTK dump wave. I think we can go like hash dump vars 0. We can do a main TB. So that's just we have. It's just so we're using this and we're like used to using it. So because it should open malformed statement. Yeah, so that gives us the remainder TB, and we can get the clock count. We can get the actually we want to go into the device under test, and in the device under test we should get the register value, and you can see here, this is amazing. You can see 9A B C D E F 0 1 2 3 4 5 all the way to F. So it's actually doing the thing that it's supposed to do. And then if we close this, that's cool. So yeah. Yeah, so we made a simulation, we made a module, we made everything that goes with that. Git status, git main.tb, git diff dash staged, git commit dash m, dump vars for GTK wave simulation. GTK wave signal observation signals. Git push. No, git. So let's go back. Let's go back here. That copy. Push dash u origin main, and then up. Git branch. Git branch dash and main, and then that should be good. And then the other thing we need to do is actually do this, take this and put it in the description of the video. Yeah, I really wait. So stream settings and edit, and the code that we're working on. Can we see? Yeah. Code we are working on, and that's in the description of the video. Well, thank you everyone. Thank you so much for hanging out with me. This has been an hour and a half of us doing some code and building up all of this stuff. I'm really glad to have done this. I'm really glad to have discovered this. So tomorrow what we're gonna do is we're gonna try and go through this the advanced reading here, which is the micro pipelines. I'm gonna try and read this, and we're gonna try and see we're gonna try and learn what about micro pipelines and how they work and whatever, and all of these things and pipelining. And this is going to lead us into asynchronous stuff, which is going to be insanely good, so that we can actually start building real FPGA solutions that are going to really help us go forward. And this brings in clocks, this brings in timing, and all of those things that we're going to learn as we go along and kind of advance. Again, thank you so much. My name is Zach, and we just built a binary counter module, and along with the test bench to go for it. and we fumbled along with the test bench, and we found out that there's some intricacies that we do not really understand. However, I'm going to take that question to a bigger group or people who understand digital design far better than me, and we're going to observe what can happen there. Thank you so much for coming and sharing with me, and till next time, I dare you to be very daring and try things harder. Thank you, and cheers.